Hello and welcome guys. Now in this video we will be talking about handling multiple classes. So how logistic regression deal with multiple class classification problem, since it is limited to binary outcome, that is two classes. So logistic regression is a binary classification algorithm that model the probability of event occurring, that is binary outcome, given one or more predicted variable. However, there are several ways to extend logistic regression to handle multi-class classification problem. Though you can see that one versus all, or one versus rest method. So what it says, this method involved training binary logistic regression model, where each model is trained to distinguish one class from all the others. For example, in a problem with three class A, B and C, we would train three binary logistic regression model: A versus B plus C, B versus A plus C, and C versus A plus B. Okay, during prediction we would apply each model to the input data and choose the class with the highest predicted probability. Another method will be multinomial logistic regression. So this method extends binary logistic regression to handle more than two classes by modeling the probabilities of all classes simultaneously. So in this method, logistic regression model is trained to predict the probability of each class. Then given the input variable, during prediction we would choose the class with the highest predicted probability. Another way will be softmax regression. The softmax regression is generalization of logistic regression that extends binary logistic regression to handle multiple classification problem, and it uses softmax function to normalize the predicted probability across all classes. So during the prediction we would choose the class with the highest probability as it is. In summary, logistic regression can be extended to handle multi-class classification problem using various methods such as OVA, multiple logistic regression, and softmax regression. Now to close logistic regression part, just wanted to clarify one more thing that I have just discussed in the previous video also. So like I talked about, however in some cases the relationship between the predictor and outcome variable may not be linear, right? I mean, see this data. I mean, this is not separable. I mean, even if you create a line from here, still you have some point, plus point here. In this region we have some yellow dots also. Okay, so I mean, which means that the straight line will not be able to accurately separate two classes. In such cases, linear decision boundary can non-linear decision boundary can be used instead. So non-linear decision boundary can be represented by a more complex function. What we need to do is we need such as quadratic function or a cubic function or a other non-linear function. I mean, this function will allow us to relationship between the predicted variable and can result decision boundary that is more flexible and capturing more non-linear pattern in the data. Okay, and those complex function will let us classify the two classes like this. I mean, it won't going to fit all of the point, but it will somewhat do something like this. Not like this, sorry. Let me remove it. So it will do something like this. Okay, so that most of the plus class will be here and most of the yellow dot class will be here, and this cannot be possible using straight line, right? So straight line will be like this or like this. So we need some non-linearity in our equation so that it will be able to solve such issues. Okay, and moving forward we will see that some of the algorithm may overfit such type of data, will process the separation will be like this, and this is what overfitting look like. So overfitting will be like this. Okay, I mean, good separation will be like this. Okay, and underfitted line will be like this. Okay, so we'll talk about these terms in the later videos more thoroughly, but this is what I wanted to